Welcome to the Space Telescope Public Lecture Series. Tonight's talk, Hunting the Stellar Undead by Gregory Sivakoff of the University of Alberta. I am Dr. Frank Summers from the Space Telescope Science Institute Office of Public Outreach. And as always, I want to thank our wonderful tech team, Gary Gilbert and Grant Justice, who bring you these webcasts. Upcoming. Well, actually, there's nothing upcoming right now. In 2025, we will do changes to the public presentations. We've had some significant funding changes over the last several months, and the current status is that the public lecture series will go on hiatus starting next month, January 2025. Now, I did find out today there are plans in the works to bring back some public lectures, possibly only 4 per year, and on Webb Space Telescope topics. This is preliminary. We will find out how this develops over the coming months, but you can find out the status of it by going to our website, www.stsci.edu/public-lectures, okay? And on this web page is where we will announce what the transition will come to in the coming months when we have a fully formulated plan. Currently on this web page, you can find links to our webcasts, and you should know that we have over 100 public lectures recorded and in not only on our YouTube playlist, but also in our webcast archives at the Space Telescope Science Institute. On the other side, you can subscribe to our email announcements. We will also send out information of the changes to the public lecture series via our email. Also on our website are all of the lists of the upcoming and previous lectures. There are unfortunately no upcoming right now, but there are a huge list of previous lectures that you can go to. And for each lecture, there is a description of the lecture, a date when it was recorded, and also links to the STSCI webcast and the YouTube webcast. Announcements, as I said, sign up on our website. You can subscribe to our YouTube channel, youtube.com/Hubble Space Telescope, where you'll get the new video notices and reminders of live events. However, also due to these funding changes, we expect to rebrand our YouTube channel from Hubble Space Telescope to a more generic name. So don't be surprised in the next upcoming months if the name of our channel changes. It'll still be the same channel. It'll still have the same content, but it's going to undergo a name change for a more generic branding of it, okay? Also, if you have comments or questions, you can still send them to an email address, publiclecture@stsci.edu. Finally, I always remind you of our social media accounts for the Hubble Space Telescope, the Webb Space Telescope, and for our institute, the Space Telescope Science Institute. We're on Facebook, we're on X, we're on YouTube, and Instagram, so you can follow along there. All right, and now, news from the universe for December 2024. And our first story tonight is Hubble and Webb, a pair of ghoulish galaxies. Actually, I'm going to do 3 stories tonight. I've typically only been doing 1 or 2 lately, but I'm going to do 3 because I have 3 cool stories that compare Hubble and Webb images. So the first one is a pair of galaxies, and these galaxies go by the name NGC 2207 and IC 2163. These are just catalog numbers, okay? But it's kind of cool because these got these 2 galaxies that are overlapping. Now, you might think that these galaxies are interacting, that they're crashing together. But what you don't see is evidence of a strong interaction. You don't see one galaxy being pulled apart like taffy, okay? You don't see those telltale signs of interaction. So what's really happening is the 2 galaxies are currently one in front of the other, And you can see that if you look here in the center, okay? You look in the center, you can see this dark dust lane from the front galaxy passing in front of the other galaxy, right? And that shows you that this stuff is in the foreground in front of that other galaxy. The two galaxies aren't interacting yet. They probably will interact. I mean, as an astronomer, I think like it's obvious they're going to interact. They're just too close together for them not to be gravitationally bound, eventually merging and forming into one galaxy. All right. So this is what Hubble saw in 1999. So let's take that image, let's spin it around a bit, and let's recolor it to emphasize those star forming regions. You see all those blue, okay? That's what places where the stars have just been formed in that foreground galaxy. Lots of stars forming in there, okay? And then you can see that the dust is even darker here. That dust that goes in front of that background galaxy is even darker. Why do we want to do that? Because we're going to compare it against the Webb image, and this is the Webb mid-infrared image that pulls out that dust, okay? That dust that is dark in the Hubble image is glowing in the mid-infrared. So if I go back to the Hubble image, okay, you can see the stars. You go to the Webb image and you get to see the dust lanes. And so by using Hubble versus Webb, we get to see both pieces of it. So what if we combined them together and we gave a nice cool color to it, to the mid-infrared? Well, then you would get something like this. And this is our Halloween released with these ghoulish galaxies. Actually, I think they gave it the nickname blood-soaked eyes. Okay, so it looks like a mask with two eyes for the centers of the galaxies, and you get all the red around it and everything. But it's really kind of cool. Okay, if you look at this image carefully, you can see like in this bottom region here where there is a red outline around these blue star forming regions, or just at the top above the center of the front galaxy. You can see the red outlines to those star forming regions. And over here on the right, you can see that as well. All right, and so that shows you that the stars form in these dust clouds and then create pockets within the dust clouds. And so you get the outline, the dust outline around these star forming regions. And it's an example of how Hubble and Webb work together to explore different aspects of the same object. Second one we're going to look at is a smooth stellar disk. Okay, let me start with, all right, what we're going to, if you look in the night sky, if you observe it much, you may know these three stars, Vega, Deneb, and Altair. These are three very bright stars. They stand out such that they're an asterism called the Summer Triangle. Okay, and that's because in the summer, at least in the northern hemisphere, these three stars are up high in the sky at about 9 or 10 p.m. I actually went out to check the mailbox about an hour and a half ago, and there they were standing right in front of me. Like, oh, okay, there's the Summer Triangle. What's important about this Summer Triangle is Vega. And if you look in detail at Vega, you get it blown out because it's a bright star. It's an A star. It's much, much brighter than our sun in absolute magnitude. And it, it's a very bright star in the sky. It blows out. You can't really get much by just taking an optical image, except if you do it in a special way. Well, first thing, you can look at this in infrared light. Okay, and so this is a Spitzer image in infrared light where it doesn't blow out because as an A star, most of its light is in the optical and even towards the ultraviolet. So it's very bright, but it's at shorter wavelengths. As you get out to, I think this is the 70 micron observation in Spitzer in the mid-infrared, you're actually much, much fainter and you don't blow out, right? And in the 90s, the IRAC satellite was able to tell that there was an excess emission in the infrared, that there was more light in the infrared than should come from an A star. And this Spitzer image, actually a couple Spitzer images back in 2005, was able to tell that there's actually a disk of dust around Vega. Kind of cool. You think disks around stars? Maybe there's some planets. What can we do? Well, let's take it Hubble and take a look at it with the a coronagraph, okay? So as I said, in optical, it's very, very bright. So what if you block the light of that star, right? That center circle is blocking the light of the star. You can see some of the light still spills out. You get a lot of noise in there and everything. But then you can see the other stuff around it. All right, and you see that white circle, that's the outer white circle. That is actually reflected light from dust around Vega in this disk, okay? And so with Hubble, we can tell there is a disk around it. We can't see great detail because this is reflected light, not emitted light. Dust emits in the infrared, it only reflects in the optical. So who are you going to call? Yeah, we're going to call Webb. Webb looked at this and saw this. Yeah, this is what Webb saw. I gotta say, when I first saw this, I was like, no, that's an artist's illustration. That was created in, one of these illustration programs. This isn't a real observation. But no, it is. This is a real observation in the near infrared of the disk around Vega. And what we see here is just really, really cool. We see that there is an outer disk of material, and then there's an inner disk of material, and then there's this gap in between. And these gaps are really cool because they may indicate the presence of giant planets, right? When you have a Jupiter or a Saturn, it can clear out a gap in a disk. So they looked at this in extreme detail, and they found that if there was a Jupiter or a Saturn in this gap, it would create ripples and unevenness around the inner disk and the outer disk along the edges of it. They do not find that. So there is what they call no obvious evidence for large planets forming in this disk. I think it's got to be significantly smaller than Saturn if there is an object in there. Okay, so they don't see that, and that's really weird because you see this and you're like, oh, this is really intriguing. We see things from ALMA and other ones where we see these gaps and we really are going like, oh, that really looks like a planetary system's forming. No evidence of that here. And to quote the researcher, the Vega disk is smooth, ridiculously smooth. Okay, and let's finish off with hats off to the sombrero. This is a wide scale, very deep image of the Sombrero Galaxy that I found online. And what it shows you is you've got the Sombrero Galaxy there in the center with this big, huge halo of stars around it, okay? So this is an interesting type galaxy. It's got this disk, but it's also got this huge, huge halo, which most people don't know about because they don't look at the very deep images of it. I had to actually go searching for it. They mostly see the Hubble image of the Sombrero Galaxy, which is also a little less intriguing, but it's also very intriguing too that it's got this huge disk and it's also got this huge bulge of stars here. So this is a combination galaxy. It has the disk-like features of a spiral. It has the big giant bulge features like an elliptical. And we call this a lenticular galaxy because it has those features both in strong presence. All right, and this is a wonderful image that was released in the early 2000s. And you can see there's a lot of dust in that disk there. Well, if there's dust, we want to see that dust glow, we go to the infrared. And this is the Spitzer Space Telescope image in the infrared. And you look at that disk and it shows up now here in red, but it's not quite fuzzy because Spitzer doesn't have the resolution Hubble does, right? But also look at that bulge and see how much bigger it is in the Hubble than it is in the infrared. So the infrared view of the stars gets the old stars and it's sort of shrinking and smaller. Well, let's turn this on its side just a little bit so we can compare it to the Webb image. Webb does have the same resolution as Hubble, a similar resolution to Hubble. All right, and Webb gets this. A really cool detail in that dust. All right, we go from the Spitzer to Webb, and it's just a step change in the resolution that we see in the dusk. And so we can really look into the dusk in detail. And you also see what happens here is that the bulge gets even smaller, okay, in the various things. So Here is an animated GIF that is going between Hubble and Spitzer and Webb, and you can see how the changes in the views that we get of the Sombrero Galaxy when we use multi-wavelengths, we use multiple telescopes. Okay, so the pun here is hats off to NASA for having these different great observatories that help us observe different aspects of the objects in our universe and really just learn more about what's going on out there. Okay, our speaker tonight is Dr. Gregory Sivakoff of the University of Alberta. Welcome, Greg. He did his undergraduate work at Brandeis and then did a Fulbright scholarship to Jodrell Bank in Manchester, where he got his master's in radio astronomy. He came back to the US to do his PhD at the University of Virginia. He's a Wahoo. I'm a former Hokie. Okay. Those aren't fighting words. Okay. Let me just say, they're just rivalry words that sound like they're nonsense words. And then he did a couple of postdocs, one at Ohio State University and one back at University of Virginia, before moving to Edmonton, Alberta, and the University of Alberta, where he is now a professor and has been so for I forgot how many years. You've been in Alberta. I think you're muted. Or at least I can't hear you.
13.
13. I knew it was like 10, but I didn't know anything. All right. And one interesting thing about him, I always ask for an interesting thing about my speakers, is that he spends a lot of time in the Minecraft community, running some shared servers and helping people who are streaming and everything, and is involved in this. And so I've never actually done Minecraft, but I've seen my kids play it. That's another universe to explore, right?
Indeed.
All right, ladies and gentlemen, Dr. Greg Sivakoff.
Well, thank you very much. It's my pleasure to be here. And tonight, I'm going to be telling you a tale that perhaps might have been slightly more appropriate a few months ago, getting ready for Halloween, but we managed to get it in before the new year. And today I'm going to be talking about hunting the stellar undead. And I'm going to talk about some of the vampires, the werewolves, zombies, banshees, and even dancing skeletons that are in our night skies. So first, I'd like to acknowledge that I prefer most of my science and my outreach from Treaty 6 territory in Canada. This territory was a traditional gathering place for diverse Indigenous people, including the Cree, the Blackfoot, the Métis, the Nakudasoi, the Iroquois, the Dene, the Ojibwe, Saulteaux, Anishinaabe, the Intuit, and many others whose histories, language, and cultures continue to influence our vibrant community. And in fact, Amisquishy Waskahikan, which is the name for Edmonton, stands for Beaver Hills, if I recall properly. If we look at popular culture, we are inundated with pictures of the undead, whether we have vampires like Nosferatu and Dracula. We have werewolves galore. Zombies and vampires and werewolves all seem to come in phases where every now and then, every 20 or 30 years, one will be more important in the videos, but they're all sort of the three standards. But if you dig deep into some of the different cultures, you have other undead that we also tend to hear about. For instance, banshees whose screams can potentially kill you, or even sometimes into the little bit of the silly, we have some old dancing skeletons. I like to not take myself too seriously either. As an astronomer, I hunt the stellar undead, and the main tool of the hunt for me is the electromagnetic spectrum. So in this picture here, you're seeing some different aspects of the electromagnetic spectrum. One aspect of this is that the electromagnetic spectrum can be broken down into different wavelengths or frequencies. On the left of this diagram, we have the radio waves, very large wavelengths, very small frequencies. You're used to thinking about radios from your FM dial, like 100 megahertz. Then we go up into the microwave, which has the millimeter and submillimeter wavelengths, and the frequency grows. Next, we have the infrared. Then what we're used to thinking about light, the visible light, the optical. the ultraviolet, and then we get to the X-rays and the gamma rays. Very, very small wavelengths, very big frequencies. And we have different things that we're used to thinking about in terms of where these different tools come into play. But when we think about astronomy, a big thing we have to think about is our atmosphere. And it turns out that our atmosphere is opaque to most frequencies except for radio waves, visible light, and certain ranges within the near infrared. So in order to hunt different objects in the night skies, astronomers have to use a range of tools that not just span this entire wavelength regime, but they also have to use tools that are going to go above the atmosphere as well as tools on the ground. So I'm going to talk about some of the tools we use in particular for the stellar undead, and first I'm going to talk about the tools above our atmosphere. When I talk about a satellite, even if I'm not talking to Space Telescope Science Institute public lecture series, I have to mention Hubble first. It is the telescope that most people think of when they think of a satellite. The Hubble telescope has been absolutely groundbreaking. It observes mostly in the visible light, as well as a little bit in the near infrared and a little bit in the ultraviolet. And this is a mission that NASA has led, but has lots of other countries, their science agencies are helping or helped develop instruments and helped run aspects of the Hubble Space Telescope. These days, we also have, like we just heard about, the Webb Space Telescope. Here, the scale gets much larger. While the mirror of the Hubble Space Telescope is 2.4 meters, the mirror of James Webb Space Telescope is more than 6 meters. Much bigger telescope, and much different in this way in that it is mostly focused on infrared light, mainly the near infrared and the mid infrared, as well as some of the redder parts of visible light. And because this telescope is operating in a different regime, there are different things we have to do. We have to keep this telescope exceptionally cool, which is one of the reasons why you see those solar shields, which are protecting the instruments from the area which is getting a lot of the sunlight. But we also can look at wavelengths that are completely inaccessible from the ground. And when it comes to the stellar undead, X-ray telescopes have to largely be in space or launched on rockets or balloons that reach very high altitudes. One of my workhorse instruments is not one of these very large telescopes, these great observatories like the Hubble Space Telescope, like James Webb, like NASA's Chandra X-ray Observatory, but instead a smaller mission led by NASA, the Neil Gehrels Swift Observatory. Mainly an X-ray instrument, this also has an ultraviolet optical telescope. But this instrument is really handy for those of us who hunt the stellar undead because it's a very nimble instrument. So if we get some hint from one of the instruments on board that there may be a new stellar undead out there, we can quickly tell them to point the instrument and we can hunt down our new quarry. But the type of telescopes you have in the X-rays can be very varied. Another smaller mission compared to Hubble and the Webb Space Telescope is the NuSTAR telescope. This telescope is an absolute marvel of engineering where in order to focus the high energy X-rays that NuSTAR looks at, we had to extend essentially the camera on a very large boom away from the optics that reflected the light back towards it. But we don't just have to use satellites. As a matter of fact, we've actually installed instruments on the International Space Station to do science. So the nicer instrument here can point at a variety of different bright X-ray objects and time their variations very precisely. But it's also not just NASA that's leading these missions. For instance, the Japanese lead another telescope on the International Space Station, MAXI, who's been also very responsible for identifying a large number of the stellar undead. In optical and visible, we've often gone to space because that allows us to avoid problems on the ground that limit the detailed images we can see. And this is why those Hubble and Webb images you've seen are so detailed. In X-rays, we have to. But we still also definitely use observatories on the ground to hunt the stellar undead. If we go to the very smallest wavelengths now, So from the X-rays on the right of this diagram, the optical towards the middle, and the infrared towards the middle, if we go to the radio, it turns out that radio waves are so relatively large that it's hard to make detailed images of them. But we have tricks up our sleeve. So for instance, one of the big tricks we use is we don't use single radio telescopes. Instead, we use arrays of radio telescopes. The other thing you'll notice, radio telescopes look a lot different than the satellites or the optical telescopes that we're used to thinking about. Instead, radio telescopes look a lot like satellite dishes. That's because satellite dishes are really radio telescopes. In this, the Very Large Array, and a US-based observatory led by the National Radio Astronomy Observatory, has been a workhorse in radio astronomy through multiple upgrades over the years, allowing some very precise images that you can make at resolutions that are sometimes similar to the resolutions you get with the Hubble Space Telescope. But here we do this by stretching instruments kilometers away and combining their signals together. We also sometimes use large singular disk telescopes, and these telescopes may look a little small here, but each one of these telescopes is about 25 meters in diameter. Sometimes when we're studying the stellar undead, we also use larger versions of these, like the Green Bank telescope, which is over 100 meters in diameter, or at least that's its effective area. But we can also look at other parts of the electromagnetic spectrum similarly. Like in radio, if we go a little bit higher in frequency, we can use the Atacama Large Millimeter Array to look at microwave light, the millimeter, the sub-millimeter regime. You can also use single dishes to monitor how bright things are, but if you want to see details, almost the thing you use. And of course, we also use the classical optical telescopes. For instance, the VLT telescopes, that may look like a relatively small facility until you realize that the telescope that you may see in the enclosure here is a 10-meter class telescope. These are very large telescopes. This is one led by the European Southern Observatory. It turns out that when we're studying the stellar undead, we often have to take this multi-wavelength approach. Different parts of the spectrum are going to tell us about different aspects of the stellar undead. Why do I keep on calling them the stellar undead, though? Well, we have to first think about the lives of stars before we can get to their afterlives. So this is a wonderful picture that the NASA's Chandra X-ray Center put out, which sort of talks about the entire evolution of stars in one diagram. On the axis at the bottom, you have time increasing from left to right. All the stars in this image start off as protostars at early times. On the axis vertically, you see the mass of stars. We're starting at low mass stars at the very bottom, going up to the most massive stars towards the top. And while all the stars start as protostars, as they evolve, they actually turn into different classes of objects. You have the supergiants for the massive stars, and the more similar stars to our own sun for the less massive stars. You may have even heard the term a red dwarf. Well, our sun is a type of red dwarf, but when you go to even lower masses, they get even redder. For most of a star's life, you have gravity that is pulling it in, but you have the energy resulting from nuclear fusion in the center of the stars that's providing support against gravity. And so the stars stay stable for relatively long periods of time. Our own sun's lifetime in stableness is 10 billion years, and we're only about halfway through that. But there's something that's very interesting about stars. The most massive stars live fast and die young, but the most massive stars may only be able to support themselves against collapse for millions of years. And millions of years is a blink in astronomy terms. Now, it turns out that when you no longer have support from the core, you wind up starting to go through some collapse and some expansions where you might have some temporary support from outside the core in, for instance, the red giant phases, which we see sort of towards the center of this diagram. But eventually, you're going to run out of all options for nuclear fuel for your massive stars and even for your sun-like stars, and gravity will eventually win. At that point, the star is essentially dead. It's never going to be quite a star like it was beforehand. The stars of different masses die as different objects. Sun-like stars will die and form an object called a white dwarf, where the mass of a white dwarf, instead of being the size of the sun, it gets squeezed about 1,000 times smaller to about the size of the Earth. If you go to slightly more massive stars, there's nothing to stop that support at the size scale of the Earth, and instead things get even more dense, and you get the mass of the sun in the size of about 10 kilometers, about the size of a typical city. But if you go even more massive, well, nothing can stop it, and you may form a black hole where, in theory, you get the mass of a star in an infinitesimal point. The black holes, the neutron stars, the white dwarfs, these are the deaths of stars. But not everything that dies stays dead. And so today I'm going to take you through some of those stellar undead. Before that, I'm just going to talk a little bit about why. Well, I'm from Alberta. Alberta is known for producing a lot of energy, but I like to always remind people from Alberta that gasoline is not exactly the best energy source. So if you take a kilogram of gasoline, you convert it to energy, you can take your hybrid Toyota Prius and you can run it about 12 miles. The best thing you can do is you can use nuclear reactions on a kilogram of fuel, and then you can take that same Prius all the way to the moon. But it turns out that the best way of generating energy is just allowed to fall into something that's very compact. And all the stellar undead are much more compact than the stars they came from. If I could have a kilogram fall onto a stellar mass black hole, well, there you'd get about 70 times farther than the moon. So these are actually the best energy generators in the universe. Now, are we going to be able to ever use that energy? Not for a long time, but I always like to joke that I'm doing this to understand energy. But I'm also doing this really to understand the stellar undead because they themselves are interesting. The first bit of the stellar undead I'm going to introduce you to are called X-ray binaries. What is an X-ray binary? Well, in this image here, on your left, you see a regular star. And there seems to be some material that's getting pulled off the star onto a disk around another object. It turns out at the center of that disk, what we call an accretion disk, is either a neutron star or a black hole. And that neutron star or black hole can feed on any material that gets into the interior disk. So I like to think about X-rays as being these stellar vampires. Now, one of the other things you'll see from this particular image is these long jet-like features, roughly perpendicular to the narrow type features relatively perpendicular to the disk. In astronomy, we call these things jets. And it turns out that these disks of material and these jets of outflows are actually a fairly common thing that you see throughout astronomy. Protostars have disks and outflows that are collimated like jets. It turns out that supermassive black holes, like those that may be in the center of galaxies, also seem to have some accretion disks and jets. So why would we hunt stellar vampires? Well, it's not to put a stake in them so that they can hunt other stars. It's because we want to understand the process of how objects can eat and how they can burp. So normally for a lot of these stars, material in the accretion disk may not actually go all the way to the center. And there the vampire is feeding very, very slowly, very daintily. But occasionally the stellar vampire, well, a meal gets delivered to them, and during that mealtime, they really feast. And during that mealtime, things can change to both the disk around it and the jet material. My particular research is trying to understand why it is that jets get launched and why sometimes those jets stop getting launched as the stellar vampires eat. Now, it turns out that these things are interesting objects, so scientists go after them. But it's not just a professional scientist that is interested in these. So I've been involved with the American Association for Variable Star Observers, AAVSO. And oftentimes when an object goes into an outburst, we actually let AAVSO members know about this, and citizen scientists take it upon themselves to observe stars for us from the ground. And there's a wonderful quote in an AAVSO press release on one of the objects I've studied most, the X-ray binary called V404 Cygni. And this encapsulates some of the wonder we have in astronomy. Referring to V404 Sig, Bill says, "It's not a star I normally observe. But when I saw AAVSO Alert Notice 520 requesting observations, I decided to get on it. The observations made on this target were immediately exciting. Seeing changes greater than 1 magnitude in less than an hour, and some high-frequency changes occurring in the minutes range was a wonder to see. I kept imagining how this target must be going through unbelievable eruptive changes." So one of the things we learn about stellar vampires is that they are very quick eaters, and what they're eating, how quickly they're eating, can change on very rapid timescales. This means that not only, and some of these sources are so bright that with a relatively decent sized telescope that you can purchase, you can actually follow these objects in detail. I hate to call AAVSO members citizen scientists. I love calling them citizen scientists. I hate to call them amateur astronomers because their work is anything but amateur. It's of a professional quality. But I like to emphasize that you too can become a hunter of the stellar undead. Now, why else might we be interested in studying these stellar vampires? Well, it turns out that black holes and neutron stars are some of the densest objects in our universe. And that means we get the ability to study the strong gravitational regime. This is the regime that Einstein's theory of general relativity best describes. And there's some very interesting things that go on. So this is an artist rendition of what's going on in V404 Sig. And one of my collaborations, great observations of this, was studying the radio jet and finding that on time scales of less than an hour, the radio jet appeared to be moving side to side. We actually could use arrays of radio telescopes and see the ejecta moving out on different trajectories. We use telescopes from the entire US to get great detail, more than Hubble can see. And we saw these little blobs coming out, but the direction they came out were changing. And so this is the picture that we think is going on. We think there has to be a jet of material that is essentially rotating like a spinning top does towards the end of its rotation. In order to get this, we need to have a puffed up disk close to the black hole. In order to get that puffed up disk, well, it turns up that we need to go to theories to understand why this is actually occurring. And there's a theory that was put out, which is that a black hole that is spinning can actually drag the very fabric of the universe around with it, space and time together, called space-time. And we think that the fact that we saw this jet oscillating back and forth on rapid timescales meant that we were seeing a black hole actually affect the space-time around it. And this is one of the best observations we have to date that frag dreaming, as it's called, can occur. Sorry, frame dragging. So I think stellar vampires are interesting, but they're not the only undead. The relatively intermediate mass stars that didn't form black holes or didn't form white dwarfs, they form neutron stars. And neutron stars were actually some of the first stellar undead that we were able to identify. And the reason why we were able to identify them is that some neutron stars that spin have beams of radio emission. And if you just happen to be at the right orientation relative to those beams, what you wind up seeing is pulses of radio emission occurring exceptionally regularly. Now, astronomers were not the best at naming things, so instead of calling these things some really cool name, we started by calling them pulsating stars, and then we got lazy and called them pulsars. And that's the name that stuck. But, if I tell you the truth, as a joke, the very first names of these objects were LGM. The first two were called LGM-1 and LGM-2. LGM stood for Little Green Men. It was a joke. We didn't think they were actually alien signals, but I would have loved if we had kept those names. Again, I like whimsy a little bit more than sometimes the strict scientific names. If you think about this, a neutron star is undead. Nevertheless, it seems to keep on going in certain cases. I'll tell you that neutron stars are exceptionally important in astronomy because they act as very regular clocks. When these were first discovered, these were basically as accurate as the most accurate clocks we had on Earth. Today, a few Earthbound clocks can outdo pulsars, but there are certain types of pulsars that are so precise as clocks that we actually use them to test more aspects of Einstein's theory of relativity. For instance, one of the best studied neutron stars is not actually a single system of neutron stars. It is two pulsars in the same exact system orbiting around one another. And because we have not just one, but two different clocks in this system, we're actually able to test other predictions of Einstein's theory of general relativity at extreme detail. Now, studying Einstein is not the only thing we can do with the stellar undead, but it is certainly one of the things that we do best that you can do in few other ways. Now, I hate to tell you this. Well, some of these zombies are also stellar vampires. In fact, what we've seen some systems that are going between occasionally having a jet like the zombies, the pulsars having, and occasionally having a disk around them that's being fed by the neutron stars. So these neutron star X-ray binaries, you can sort of think of them as they're not just stellar vampires, they're also zombies. It's going to get worse. We've got our zombies, or we've got our vampires. What about our werewolves? Well, again, I'm going to use some data from the American Association of Variable Star Observers, because this is data that's got a huge amount of history. There's a particular star in the sky called SS Cygni. It is one of the stars in the constellation Cygnus, thus its name. And it turns out that we've been observing this star pretty regularly since before the 1900s. And AVSO has been keeping track of this. And what you can see is that the star is often quiet, and then it goes through really getting bright, then it fades. Quiet, gets bright, and fades. Now, it doesn't do this on a single time scale, but if you ask what the typical time scale is, well, it's about 30 to 45 days where all of a sudden it gets a little crazy. I don't know about you, but that to me sounds like a stellar werewolf. This data from this plot is only showing up to about 2008. This data has continued through today. I just haven't been able to make a better version of this plot yet. Well, it turns out SS Cygni is also accreting from a nearby star, so it's not just a werewolf, it's a vampire werewolf. Again, why might we be interested in studying these stars? Well, it turns out that by studying some of these stars like SS Cygni, we're actually getting at the very physics that explains how the meals in the accretion disk are able to make their way onto the plates of white dwarfs, neutron stars, and black holes at the center of those disks. This has implications for our understanding of accretion across the entire universe. It gets worse. Some of these systems are also these transient neutron star X-ray binaries. So these are stellar vampire zombie werewolves. Really, the stellar undead have much more imaginations than most of us do when it comes to undead. Now, it turns out that neutron stars and black holes, when they die, they don't just die sort of going quietly into the night. Instead, they scream their death into the night in an explosion called a supernova. And so this is an image comparing the before and after of a supernova going off in another galaxy. That little blinking light that you see to your lower left or lower right, excuse me, well, that object there is as bright as an entire galaxy, but it's really just coming from the death of a massive star. So I like to think about supernova as being these death screams. But is a death scream, sort of just a simple death scream? Is that enough to classify as a banshee? Well, before we actually consider that, I will tell you that supernova are exceptionally important. This is a picture of X-ray emission around a supernova that went off many, many years ago. The different colors here are showing different elements in the outer parts of the star that went supernova that are basically all being lit up by the much earlier explosion. And it turns out that these elements are super important because how we got here, how you and I got here, depends a lot on things like supernova. But before I go to that in much detail, I will tell you that there's a type of object that when it occurs is so much more energetic than the supernova that they're extreme death screams that I'd like to call the banshees. And these objects are gamma ray bursts. They're called gamma ray binaries or gamma ray bursts. Sorry. I mistitled that slide. I can't believe I missed that for so many years. These gamma ray bursts are much brighter than the supernova explosions, and they are seen typically in the gamma ray part of the spectrum, which I haven't talked about much till now. But what we think is going on in a lot of these cases is that we are forming a jet that breaks out of the star, and we actually wind up often seeing emission from the jet making very bright emission across the electromagnetic spectrum. So the death screams of supernova, the banshee screams of gamma ray binaries and gamma ray bursts, well, why are they important? It turns out that the explosions of massive stars have a lot to do with the elements that we see around us. In this plot of the periodic table, it is basically showing a understanding of where the elements got made. And you'll see objects like hydrogen and helium were largely made when the universe began in the Big Bang. Everything else, except for a little bit of lithium, was made later. Now, some of the light elements like beryllium and boron are made through another type of mechanism called cosmic ray fission, but it turns out that the deaths of stars are also the same material that new stars get built from. So when low mass stars die, they have large winds that often put their outer atmospheres into the interstellar medium from which new stars are formed. And the elements in green are basically coming from largely dying low mass stars. You and I are organic. We've got large amounts of carbon. It's coming from a dying low mass star. If you look in gold, what you see here are the exploding massive stars, the supernova, these death screams. And you might go, oh, well, we're carbon, but we're H2O. We're lots of H2O. Oxygen is largely produced in these exploding massive stars. So our very story is tied into this death scream. In some ways, it's a rebirth scream as well. In addition, if you can form neutron stars and merge them together, which is one of the ways we think some of these gamma ray bursts occur, they make up a large number of the other types of elements in these purple. We're still arguing the exact details for how the elements that are made in purple are there, but the exploding massive stars of supernova from the deaths of stars is one of the ways in which we make elements. And then there's one other set of elements in here, exploding white dwarfs. It turns out that white dwarfs, after being dead, can also undergo a supernova. We're not sure if that's because they get too massive or if two white dwarfs merge, but they produce other important elements like calcium, like iron, like titanium. The very story of who we are is intimately linked to the stellar undead. Now, it turns out we've been using the electromagnetic spectrum to study the stellar undead for over a century for some types of the stellar undead. But in the last few years, there's a new tool we can use to hunt these objects, and that's gravitational waves. What's shown in this picture is a simulation of what gravitational waves might look like as two black holes happen to go around one another. In green are those gravitational waves. As black holes get very close to one another, they can start to in-spiral, and the strength of gravitational waves can get faster, and the speed of those gravitational waves can get faster, and the strength can increase. And in theory, this could lead to a large amount of gravitational waves, which maybe you'd be able to detect at Earth. Now, gravitational waves are weird. In order to detect them, you actually have to detect a behavior where in one direction things are expanding, while perpendicular to that, things are contracting, and vice versa. Well, it turns out that thinking about gravitational waves, understanding the stellar undead, scientists that, with leadership out of Caltech and MIT, built the Laser Interferometry Gravitational Observatory, or LIGO. And what LIGO consists of is you can see two straight arms at perpendicular directions. These are essentially evacuated tunnels because they're going to be sending lasers down these tunnels. They bounce lasers off mirrors at the edge of the tunnel and recollect lasers back in the center. And they use special techniques to test if the length of one of these arms has changed compared to the other perpendicular arm. And doing this, they can measure unbelievably fine details and actually detect gravitational waves. And this is what actually has happened in the last decade. We have actually seen two black holes spiraling into each other and merging. I like to think of these black holes, they've got nothing else around them. They're essentially just skeletons, but they're in this intimate dance with one another until they merge. So these I like to think of as the dancing skeletons. And in fact, I'm going to play you the first data from these objects. Now, it turns out that in order to do this, we don't just use one of these observatories. There's two observatories across different parts of the U.S. So we're looking for correlated signal, and this is what we saw. And we've sonified this. So we've taken the data and the waves, and we've turned them into sound waves. All right. So what we have here is what we call a chirp. Towards the end of this, the strength and the frequency of the gravitational waves increased. So you have that whoop, whoop sound. And this was the first time we detected this, and these were two black holes merging with each other. This new gravitational tool is changing the way we think about masses in the stellar graveyard. Before, studying X-ray binaries was one of the best ways for understanding the masses of black holes. And in this particular graph, where on the vertical plot here is showing the mass of a black hole, all the purple objects are black holes that were detected in X-ray binaries. Now, it turned out with neutron stars, we could look at them in X-ray binaries, but we could also look at them in the pulsars. Those are all the objects in yellow. LIGO detects two of these objects, either two black holes, two neutron stars, or a black hole and a neutron star that merge together. And because of this, every signal we get from LIGO, we understand three stellar undead. We get the predecessor objects and what they merge to form. And if you look at this now, in blue, it showed all the black holes that LIGO has detected. For stellar mass black holes, we now know about the masses of those black holes more from gravitational waves in less than the last decade than we have learned over the entire 50 or 60 years that we've been studying X-ray binaries. They really have outdone us as hunters. So it turns out it's not just black holes that dance together and merge. You can actually get neutron stars that dance together and merge. In this case, they're dancing, they're zombies, and when they merge, they let out one of those huge gamma ray bursts. So we have dancing zombie banshees. And in 2017, we actually observed these with LIGO. So the stellar undead, well, they're important. We want to hunt them because they're telling us about things like the gravity around the strongest gravitational objects in the universe. They're telling us about universal processes like how stars eat material, whether they're stars that are forming called protostars, or whether they're stars that have already died, or whether they're just collections of gas around supermassive black holes in our universe. This very supernova are responsible for the formation, for the dispersion of large numbers of elements that are important for who we are. The hunt for stellar undead is very important. Now, as I like to say, we've heard a lot about these scary stellar undead. I like to encourage you guys not to panic. Although the stellar undead are eating away at their stellar meals, they're all very far away and we are very safe from them. Thank you very much, and I'll be happy to hear your questions.
All right. If you'd stop your screen share, we can chat for a bit and do some questions. There we
Absolutely.
go. All right. Well, that was a lot of fun. Okay. And yeah, if I could have gotten you on Halloween week, it would have been great. But I think you did a really good job of, getting inventive and being able to make the comparisons to popular culture. What I'm really impressed with, okay, is that you guys like you're working with data from a dozen different telescopes, right? Um, and that each of those is going to have that it means you're working with a dozen different archives, and therefore then there's probably a dozen different data formats on all these various things. And so like keeping track of the translation of it, I mean, how advanced have we gotten in astronomy? Can you just open up a Jupyter notebook and have Python modules to go out and grab data from all these different things and then be able to pull them together? Or how much of a work is it to really do this multi-wave, seriously multi-wavelength astronomy?
So there's a range of ways and range of difficulties for this. For instance, getting data downloaded from a resource like AAVSO or most observatories, getting that single data is relatively simple. One of the harder things is making sure that telescopes are actually looking at the objects. So a lot of the work isn't actually on the archive end, it isn't on the analysis end, it's on the organization end. It's getting a bunch of observers, a bunch of teams of observers sometimes from around the globe to say something's important, to either use existing proposals into telescopes or to write emergency proposals at 2 in the morning so that at 6 in the morning when someone in a different time zone wakes up, they may be able to say, this is important, we're going to point our resources at this. So the first bit is actually, it's a person problem. It's how do you organize all these people? And astronomy has gotten that advanced thanks to a lot of the resources we're using as an entire society. I like to call this outburst of V44 Cygni, I like to call it the social media outburst, because I actually did some organizing of this on Facebook. So we use a lot of these tools. I hate to say it, astronomers were using Zoom well before the coronavirus hit, because we like to talk to one another. And so one of the things is using all these great tools just to organize the people together. You've got teams, international teams, each team may be specializing in a different part of the spectrum. And as long as their data has been taken, and as long as their data has good time signals, you can actually merge the data together relatively simply. It depends on what you're doing. So, a matter of fact, one of the interesting things we're doing is when James Webb was put up, the thought of doing rapid timing with the space telescope wasn't on the forefront of what people thought you would do with Webb. Well, a bunch of us that are interested in these detailed studies where simultaneity is important actually have time on Webb and have developed techniques where we're actually able to use Webb in a completely unanticipated way and calibrate things so we understand the precise timings at about the second level and maybe a little bit faster than the second level in order to line things up as precisely as we need.
Cool. All right. I mean, you get a new tool, and people will say, "Hey, wait a minute, I could use it this way." And sounds like that's definitely happening here. That's wonderful. All right. So we've had questions in the YouTube chat, and
Excellent.
Grant Justice has been monitoring them a little more than I have. So Grant, welcome, and tell us what questions you've got from our chat.
Sure, absolutely. Couple questions, couple things they just want you to talk about a little more. So I'll start with a
Sure.
real
Well,
question. and
come
then-
on, it's black holes and neutron stars. They could just sit down, talk about it for another hour. Please go.
That's
problem.
fair. All right, so we get mass from two neutron stars colliding, but would we have any mass from two black holes colliding?
So, this is a great question. What happens when two black holes merge? There's two things to think about. First off, when two black holes merge, they're going to form another more massive black hole. But all this gravitational waves that are getting radiated out, well, that's taking energy away from the system. Most of us have heard E equals mc squared. Energy equals mass times the speed of light squared. If you're taking energy away from a system, you're essentially taking mass away from the system. So what happens when these two black holes merge is that they don't form a black hole that is the sum of the two masses. Instead, they form a black hole that is smaller than that. That difference is due to the energy in gravitational radiation.
All right, so you're saying that energy is radiated out from the black hole merger, but material is not spewed out through it. So the mass is coming out as energy, not coming out as particles or anything.
Exactly. And so there is this open-ended question. When you have two black holes merge, was there any material around the black holes? And so we've been hoping, but not with a lot of optimism, that when we study some of these merging black holes, we might see a signal in the electromagnetic regime due to material around the black hole. Because while nothing can escape a black hole, that's only for a very small region around the black hole. Outside of that region, things can escape and do often escape. So one of the big things that people do for looking at LIGO is when we get a black hole merger, they go, yeah, we're not likely to see anything, but this is important. So we're going to go look at large swaths of the sky to try to see this.
Right. Okay. Great.
But there's more.
Oh, you got more? Okay.
Sorry.
Keep going.
If you have a neutron star in a black hole or a neutron star in a neutron star, you do have that matter. So when the neutron star and neutron star merge, we could actually see a signal in the electromagnetic spectrum. And we're hoping that when a neutron star and a black hole merge, we'll see that too.
And one of the things that I like to remind public audiences is that many of them, perhaps even most of them, are wearing a neutron star merger result on their left finger. That gold band of your wedding ring was created in a neutron star merger. So the stellar undead are what give us our gold wedding bands.
Yes, indeed.
It was
They're
a
everywhere.
fantastic misspeak, though. I think you meant merger, but you said murder. But both really apply.
I said merger, whether I married.
Nope. You said murder. There was a slight murder in there. That's okay.
Stellar mortar. I'm here for it. So you've spoken about it a couple of times. Oh, actually, we have a follow-up. Yeah. So what about neutron stars? You just elaborated on that.
Yeah.
So something we haven't really thought about is that gravitational waves can travel at the speed of light. Do they always travel at the speed of light? Is there like a breadth that you would normally look for gravitational waves to travel? And how do you estimate that? How do you track how fast gravitational waves move?
So, to my knowledge, general relativity says that gravitational radiation travels at the speed of light. It's one of these very givens about how things work. So there are two things that always travel the speed of light: light in a vacuum and gravitational waves.
Right. And didn't they measure that the differential timing between the Hanford observation and the Livingston observation fit with that speed of light calculation, or it sort of gives you a region on the sky from which it must have come from because of
So,
that, right?
so in fact, we turned this around, and this is the same way we used arrays of telescopes to make pretty pictures. You can use arrays of detectors to better understand where things are on the sky.
Right.
And so what happens is if you look at when something occurs at one of these observatories and when it occurs at another one, this becomes a basic geometry problem. If you know the speed at which things are traveling, you can basically say it's in a certain direction. Now, unfortunately, with just two observatories, you have to look at large swaths of the sky. But these gravitational observatories are building more and more observatories, and more of these are coming online. And the reason why we're doing this is because every one we build adds more connections and allow us to pinpoint where these things are going to go off, where these things are going off. And the hope is eventually you get your gravitational alert, you know where to point your telescope, and you watch these merging neutron stars as they occur, not a few minutes, a few hours, a few days after they occur, but as they occur. That's going to be incredible.
All right, so this is sort of extreme transient observations, in that you get the alerts from the gravitational waves, which then can alert the telescopes, which can be automatically pointed and everything. So I don't know. And what always impressed me is just how precise the timing variations between all the observatories must be calibrated and everything, so that you
Yep,
can really get this down to do this right.
you can really get this down. And one of the ways you can help ensure this is using a little trick that all of us use on a daily basis these days: a little GPS detector. The global positioning satellite basically is doing this sort of in reverse. You have a bunch of different satellites that are sending signals, and based on the delays between those satellites, you know what your position is. So sometimes when we build satellites, if we're saying that absolute timing is absolutely critical, you put a little GPS detector on your satellite, and now you're able to have a very good understanding of your absolute time.
Cool.
Makes perfect sense.
All right.
Um,
Got another
what?
question there, Grant?
Yeah. We'd love to hear some more about super black hole mergers and any that you have observed or have been observed. Is this the nanograv signal?
Okay, so let me be a little bit careful here because there's a couple different things going on. We have observed individual stellar mass black holes merging. We are positive from a theoretical perspective that supermassive black holes, millions to billions of times as massive, laying in the center of galaxies, you can have galaxies merge, and maybe the massive black holes in those galaxies come to the center, eventually orbit around each other, and eventually merge. We have not detected the single signal from one of these. In order to do that, we have to basically take something like LIGO and put it in space. And there's a planned observatory to do just that. Put these gravitational wave detectors in space instead of having a few kilometers, have many kilometers between them. What Nanograv has done, so Nanograv is using these zombies, using these pulsars and the most rapidly spinning pulsars as very precise clocks, and basically using those precise clocks as basically an ability to detect gravitational waves. Because of the type of gravitational waves that they detect, they're at a lower frequency of how fast the gravitational waves are going on. And they're more in the realm where supermassive black holes would be than stellar mass black holes will be. But what nanograv can do is not detect a single black hole. They can basically detect the collective hum of supermassive black holes that are coalescing all around us and all together. So nanograv has detected that collective hum. They haven't detected a single one, nor do they really expect to detect a single supermassive black hole merger.
Right. I mean, that's one of the things about this field is that you have to go through multiple generations in order to, as we work to build this, get the sensitivity down and down and down until we can really start detecting more and more of these undead.
It's a general rule. The next generation has to almost be a factor of 10 better. Otherwise, why are you going to build it?
Yes. One of the things that, we talk about this in next generations of all these things. The one thing that impressed me is that the VLA was built in the 1970s. It's 50 years old, but it's still premier observatory with their upgrades and everything. I thought that was that's always impressive how radio astronomy has kept that working.
There's some great stories here. So
In
the 90s,
wait a minute, let me get a beer so we can sit there.
So in the 90s, there was a statement, I think this is by the NASA administrator Golden at the time, that there's cheaper, better, faster. You can only do 2 of the 3.
Yeah.
The VLA was delivered on budget, if I recall, ahead of schedule, and then a new technique was discovered soon after the VLA came online that revolutionized its sensitivity. And so it essentially delivered the impossible trifecta.
Yeah.
And it did that, and then that was able to let it coast for decades. And then only relatively recently have we gone through a modest upgrade to the telescope to use some better, newer electronics to look over wider parts of the radio spectrum to correlate that data together. And that's given it another generation of itself altogether. We are planning a new instrument called the Next Generation VLA.
Yep.
I'd like to say that the VLA is the Next Generation VLA, and what we're doing is we're doing Deep Space Nine.
Always got to have the Star Trek references,
Of course.
in astronomy. All right, Grant, we got another question?
Yeah, absolutely. Any idea which undead objects generate FRBs, which I'm guessing you'll know what that stands for?
Yes.
Okay.
So, one of the hot topics in time domain astronomy, which the Hunt for the Stellar Undead is part of, are these objects called fast radio bursts.
Got it.
And so FRBs, unlike the GRBs, the gamma ray bursts, fast radio bursts are detected in the radio, not the gamma rays. And they've got these very rapid signals. There was initially some discussion about what they could be. As a matter of fact, some of them were false signals due to microwaves. Another wonderful story at some point. But we eventually showed that a subset of these objects had to be astrophysical. And we've gone through the process now where we can actually even locate the galaxy where these are coming from some heroic work. What we think the best bet from my understanding of the material and my best opinion is that these probably have to do with neutron stars. And the reason why is the time scales are so quick that if you just think about how fast light travels, you need to have light traveling a very small distance. And the only things that are sort of likely to be generating signals over very small distances like this are probably neutron stars. The black holes, well, they've got some problems in terms of certain things just don't escape close to a black hole. A neutron star of one solar mass is just a little bit bigger than the black hole's event horizon. But it is bigger and it has that solid surface. And so there are some thoughts like, could we be looking at the equivalent of earthquakes on neutron stars? Is that what fast radio bursts are? That's one possibility. Are we looking at highly magnetized neutron stars? what we call magnetars. That's been another possibility that's been discussed. I am pretty sure they're neutron stars. Whether they're highly magnetic or not, I'm less sure about. I will tell you that in astronomy, there are a couple of rugs we sweep things under. In optical, that rug is dust. In radio, that rug is magnetic fields.
Yep.
So, yeah, magnetic fields, neutron stars, sure.
Yeah. But I mean, you make a very good point that a lot of people don't recognize that if something is varying on, I don't know, a couple hours, right? Well, light can only travel a number of like a few AU, tens of AU in a few hours, so that it has to come from something smaller than that, right? If it's varying on those timescales. And if you get to these really short timescales, it just multiply that timescale by the speed of light, you get the distance at which this object, must be at the maximum in order to vary on that time scale.
Or at least what's changing on that object.
Yeah,
So, it's possible. We're used to the Earth. It's possible to have two things on Earth changing without the entire Earth change.
exactly.
So you do have to be something very, very small. But yeah, it is incredible. Just the timescale alone, that argument. I teach my students all the time to think about this first.
Yeah.
Be sure your thing isn't going. You don't think the thing is going faster than the speed of light, unless there's a geometrical trick which allows it, and there are some.
There are a couple.
And then make sure to look and say, all right, if I just think about the time scale, what size scale does that mean, and what does this mean? It's that very first guess that you do.
Yeah. Setting parameters and such. All right, what else we got?
Next up, could you describe the final parsec problem?
Boy, if I could, I would have the solution. No, you don't want the problem. So, this is a question about the supermassive black holes. First off, what is a parsec? A parsec is a unit of distance that we talk about in astronomy. You maybe are used to hearing about light years. A parsec is about 3 light years. It's a little bit more than 3 light years. So this is a relatively large distance on certain scales. On our solar system, that's a very large distance. But on the scale of galaxies, which can be tens of thousands of light years or thousands and maybe tens of thousands of parsecs, a single parsec is a small thing. So the last parsec problem, has to do with something on a galactic scale. It has to do with supermassive black holes and how they merge. And we have some ideas of how you get supermassive black holes in merging galaxies and how you get them relatively close to one another. But we don't have that idea, and we have some idea once they're very close to one another and gravitational radiation is strong enough, we understand how they'll coalesce. But going from close to very close, we don't have the solution yet. And we call this the last parsec problem. If I had the answer to that, well, I'd have a few more papers, to say the least.
Yeah, that's why we do research, is to try and figure out those answers. And first thing is figuring out the problem that you're trying to figure out. So at least you know the problem, and that's what graduate students are for, right?
I don't get to do research; I get to organize research.
There we go.
Okay.
Got
So,
another?
how about the use of Type A supernovas as standard candles and the Hubble tension argument?
Okay, let me unpack that a little bit.
Yeah, that has a lot in it.
Yes. So when I talked about supernovas, I was talking about a certain type of supernova called a core collapse supernova. These are the supernova that form when massive stars live the end of their lives and no longer have support against gravity. There was one other I mentioned when I was talking about the elements, about merging white dwarfs or white dwarfs explosions. And these are what we call the Type 1A or the thermonuclear supernova. You don't say that at border security. So these Type 1A supernova, it turns out they have this property where they don't all have the same time scales, but if you just adjust their timescales a little bit with just the right relation, then they all sort of look the same to first order. And anytime you have something that all looks the same, or you can make it look the same, we call that a standardizable object. And if you have an object and you know that it's all the same, and if you know how bright the object should be, and if you know how bright the object is, well, now you have basically a measure of distance. And it turns out that these type of supernova are the best way, one of the best ways we have of measuring distances that are fairly distant. And these were the first, the measurements of type 1a supernova are what told us that our universe isn't just expanding, but that expansion is accelerating. Now, that's type 1a supernova. It turns out that there are other ways to get at properties of our universe, the very cosmological properties. And we often talk about the main cosmological property being the speed at which the universe is currently expanding, the Hubble parameter. And back when I was a student, we used to argue whether this Hubble parameter was between about 50 and 100, sometimes 50 and 150. Nowadays, we're in the era of precision cosmology. And we are arguing about a difference between 67 and 72. And we think that different methods are measuring this. Is that difference, because it's now, we have it so precise, our statistics aren't the problem. Is this measurement physics, telling us about physics that have changed from what we think about, or is this some astrophysics that is making our understanding of the systems not good enough to use them quite as precisely? Or is this even an instrumental, some type of systematic effect that we haven't accounted for? People get passionate about this. They will claim it's not a systematic effect in how they're doing the analysis. If I had to bet money on this, it's a systematic effect on how people are doing the analysis. It's something we haven't figured out quite yet. This is an explanation where I'm going for the simplest explanation, is that humans are fallible, as opposed to the physics of the universe is more interesting than we thought. I may be fallible in that categorization.
Yeah, and the other thing that, of course, it comes up in the Hubble tension argument is that you're looking at, Big Bang nucleosynthesis and Planck observations and everything. So you're looking at sort of a global measure of the Hubble parameter versus looking at the local universe measure with the type 1a supernovas and everything. And, that seems to be part of the tension, is it a global versus local type thing? And, yeah. It's particularly important here at the Space Telescope Science Institute because we have one of the proponents of one side working here. So
Yes.
it's a fun thing to have, cool things to discuss like
absolutely. And they're doing absolutely excellent, incredible work that we're now arguing over such what formerly would have been an unbelievable thing to think that we'd be arguing over a difference of less than 10%.
Exactly. I was when I got my PhD back in the 90s, it was like, oh yeah, 10%. Good luck getting down to that. Good luck getting your error bars down to it. Now they got the error bars down to just a few percent, and so they're arguing about a 10% difference. So, all right, Grant, one last question if you got one.
MOND proponent.
Ah.
I don't know what this means. I'm guessing it means something to you guys.
It means something to us. Yes, go ahead.
What's the question?
Are you an MOND proponent? Or
oh God, no.
What do you think of MOND?
Okay, so first off, what is MOND?
Thank you.
MOND is modified Newtonian dynamics. And if I'm remembering properly, I sometimes get the D wrong. And essentially, we're coming up with, when we're talking about gravity, how do you explain some of the properties of gravity? And there was a big issue, and there is still a big issue, in understanding the gravity we see from stars as, let's say, they orbit galaxies. And what was shown originally was that the distribution of these indicated that there must be some unseen matter that we didn't know about, or our understanding of gravity at the scales here that we were talking about were wrong. One of these camps is talking about dark matter. The other camp is talking about modifying gravity somehow, and these largely get put under modified Newtonian dynamics, MOND. My problem with most of what's gone on in the MOND world is that as better data have come in that have invalidated past hypotheses, rather than giving up the theory, they say, no, the theory is right, but we need to add in something else. So there's an observation where we had two clusters of galaxies merging. The two clusters of galaxies had some hot gas, and hot gas, when it merges, well, it doesn't pass through one another. But stars, it's weird, the stars are so spread out that the stars essentially pass right through one another. And our theory of dark matter was that dark matter passes through each other. And we looked at where mass was, we looked at where gas was, and we looked at where stars were. And when we put this together, this is part of the bullet cluster and some other clusters.
Yep.
It really seemed to be, to me, it seemed to be the nail in the plank for MOND, that MOND was over. So now MOND is still around, and now it's MOND plus dark matter that you often see. First off, I am mostly an empiricist. And so that's the first thing. The next thing is I'm an alchemist. I try to apply Occam's razor whenever possible. Occam's razor basically says if there's sort of two equally possible explanations, take the simpler one. That's the one that's more likely. And so my general opinion is, although we haven't found out the particle basis for dark matter, I think when it comes to galactic scales, dark matter describes gravity well enough. And we do not need to modify Einstein's relativity or Newton's relativity, because at this scale, it's sort of the same thing, in order to understand this. I can be wrong.
Right. I mean, I agree with you totally on this and everything. And I mean, if I were going to be picky about something, it would be more about dark energy, right? Because since 1997, we've known that it exists, and it just never, I've never fully gotten comfortable with it because it doesn't, there's physics there that doesn't fit and such. So it's going to take me another decade or two to really I'll accept it, and it's the best working hypothesis for everything we're doing. It just still doesn't feel comfortable to this old guy.
I'll be honest. I mean, when you think about dark matter and dark energy, the first thing that we're basically saying is that most of the things that we're used to thinking about matter, most of what we understand, is a very small fraction of the energy density of the universe.
Yep.
So we understand a very small fraction of a very small fraction of a very small fraction of the universe.
Yeah.
But
All right. Okay. Go ahead.
But there's different fields. They're trying to get at understanding what the physics is behind dark matter. Particle physics, if particle physics can detect the particle behind dark matter, that's A, Nobel Prize, and B, revolutionize what we do.
Yeah.
Real question is going to become, let's say they don't in a decade. Now what do we do? I don't know.
Yeah. Well, that's the wonderful wonder of science, is that we keep exploring, we keep finding out new things, and we keep finding new questions too. So the adventure of science is those discoveries over the years, and it's wonderful to look back on this. And so let me thank you. This was a wonderful exploration through the dark world of stellar undead here. I will say to the audience, I don't know when we will be back. It's sort of like that song, "We'll meet again, don't know where, don't know when." But thank you all for watching and supporting the public lecture series. I look forward to seeing you online eventually again. All right, take care and thank you and good night.